Thank you, Bob. Don't worry, we're not going to keep swapping gyms all evening. It will reach its limit eventually. So I'm going to talk largely about Chapter 2 of the book, which was concerned with giving an overview of things to consider when analysing innovation in energy systems, which has become an increasingly global business conducted by multinational firms, and some of the considerations for national policy that flow from that, which again tend you towards the role of collaboration as well as towards lessons for national policy in individual countries. As Jean-Charles was saying as well, this is one of the ways in which energy systems start to get linked to broader discussions about the global economy as a whole, because innovation does have the power to actually be the driver of new industries and changes in economic structure. So this is one of the ways in which the energy system links to broader economic trends. The book itself, as Paul was saying, has a number of other chapters that look in detail on innovation in areas like solar, wind, demand-side technologies and networks. So this is very much an overview. Nice to see many of the authors of the other chapters in the audience, so that's where you'll find the detail on that. So in my 10 minutes, I just wanted to make a couple of conceptual points about how to understand innovation, talk a little bit about how we actually measure innovation, if governments and companies are trying to understand what's happening, where it's going, is it going fast enough, and then I'll end with some pointers for policy and some lessons for policy. So a couple of things on how we might understand innovation. So we're very used in, certainly in my world, my corner of academia, talking about energy innovation systems. So instead of talking about just single technologies, thinking about how they fit into systems of energy, but also systems of innovation. At the top of this slide, which is taken from the Global Energy Assessment that Paul mentioned earlier, is a kind of traditional linear model of innovation, which certainly was around for a lot of the 20th century. The idea basically that you do research, usually in laboratories by people in white coats, and then that things pop out which then get further developed, they get demonstrated, perhaps scaled up, and then they get diffused in markets. It's very much a linear model, as it says there, from the laboratory through to the market. But as people have studied this in a great detail, and actually industry practice as well, it's become clear that actually that's not how innovation happens at all. And the bottom diagram, although it's a very much a simplification of the real world, is closer to the way in which innovation happens. So yes, we do have these distinct stages, and these are true of many energy technologies. Some are at the research stage, some are at the demonstration stage, and some are diffusing, like solar PV, for example. But there are very big feedbacks between those stages. A lot of innovation happens at market deployment stage, as well as in the laboratory. So the cost falls we've seen in solar technology isn't largely due to people in laboratories inventing new solar technologies. It's to do with innovation in processes of manufacturing those solar cells and getting the cost of that manufacture down through mass production and scaling up in places like China. The bottom diagram also emphasises that actors are important and networks and institutions. That's really code for saying, well, yes, companies matter, so do public sector research institutions and private ones, but also governments, crucially, can set policy frameworks which can influence the direction of these innovation processes. So I think that's really important too. I think a final point, which the diagram doesn't really illustrate as well, is that all innovation is not technological. What we study in the book and talk about, particularly on the demand side, is the role of social innovation too, the way in which you arrange things differently, the way in which people's behaviour may have to change, or we may need new business models in order to get new types of innovation to work. My second diagram, again I'm not going to go through it in detail, is one of the famous or notorious, depending on your taste, McKinsey curves, which line up all of the abatement opportunities. This is a global curve, and say what their costs are going to be. So on the left-hand side, you have all the so-called negative cost options, which should be implemented anyway, at least if you're a dry theoretical economist. And on the right-hand side are options which will actually cost a lot of money in order to abate tons of CO2. I'm not going to go through all of these, of course, but I'm using the diagram to illustrate three basic points which were in the boxes on the diagram. First is that this sort of diagram is used to advance the case that there are many negative cost measures that should simply be invested in, particularly on the demand side of the energy system. So energy efficiency technologies, which will save people money and businesses money, often in a very short space of time. But often the problem is that they need upfront investment, and there are a whole range of well-documented barriers to investment, both in the individual level, the community level, and the industry level, which stop them being taken up. So there's a case for policy intervention to accelerate the uptake of those measures, to overcome the cost and financing barriers, but also some of the points that Jean-Charles was talking about with respect to risk of new technologies compared to incumbent technologies. The second point at the bottom there, often we need new infrastructures, that's network infrastructures, in order to realise the potential of newer low-carbon technologies. So if we're, for example, shifting from gas-based heating systems, like we have in the UK largely for most households, to electric-based heating systems, or to hydrogen, or to biomass-fueled heating systems in some areas, each of those has implications not only just for the end-use technology and the user of those heating systems, but actually for the network infrastructure that we need to deliver the energy to deliver the heat to those homeowners. And that requires investment. And there's often lock-in to existing infrastructures, partly because those costs are sunk. They've been paid for over decades quite often, so it's easier to reuse them. But also that the laws, regulations, and the companies are set up to make the best of those network infrastructures. That we have economies of scale, so it's easier economically to use them. So when you try and change those infrastructures, it can be incredibly difficult. So infrastructures are important too, not just individual technologies. Thirdly, not all of these technologies are at the same stage. They're often talked about interchangeably, whereas on this slide are technologies which are fully commercial. You can go and buy them, and they're actually fairly cost-effective now. LED lighting, increasingly, for example. But there are technologies which are still at the demonstration phase. I'll just pick out CCS, carbon capture and storage, on the right-hand side there. That's still being demonstrated at scale in North America and a number of other countries, including, potentially in the future, the UK. So those sorts of technologies, investors still face a lot of risk and a lot of cost. It still needs to cross what's called the valley of death in the innovation literature in order to reach commercial deployment. So you need different types of policies for those than you do for the commercial technologies. So secondly, how do you actually measure what's going on? First, the temptation is to look at research and development spending, the input of the energy system, the front end, if you like. This shows some more IEA data to build on what Jim Ski showed. This is R&D spending of all the IEA member countries that reported R&D spending over time since its foundation in 1974. 2014 data is incomplete, so don't go away with the impression that R&D spending has suddenly taken a nosedive in 2014. It's not actually complete data. You can see there have been peaks and troughs in that, largely following the trends in the oil price, which is the black line on the same scale. So when oil prices are high, we've tended to have a lot of R&D spending. When they've fallen, R&D spending has fallen. But also, in the most recent years, the financial crisis led to a lot of stimulus spending, and that accounts for the very sharp peak in 2008, 2009, and of course the advent of climate change and concern about that has driven R&D spending trends. One final point to make on this before I move on is notice the difference in balance of spending between the left-hand side, where the orange really dominates, that's nuclear power spending, R&D, and on the right-hand side where we've ended up, where there's a much better, you might say, or at least a more balanced portfolio between demand, nuclear power, renewables, system technologies, and so on. So there's been a real rebalancing of spending in many countries over that period of time. A final point, because I haven't got a slide on it, is, and something that Jim Ski's work has revealed, is that if you look at private sector spending, not public sector spending, you get a very different pattern, at least according to the data we can get hold of, which is private sector spending on R&D is still dominated by fossil fuel R&D. So the innovations that gave us things like the shale revolution are still dominating private sector spending. It's not renewable energy. So you have these rather different worlds, depending on which industry you look at, between public sector and private sector. Another way of looking at it, just before I move on to that, I wanted to find some data on China, because China is missed off the IEA data. It's very hard to get hold of reliable data for China. This is quite old because it only ends in 2008. You can see even around 10 years ago, Chinese R&D, as reported, had started to overtake R&D spending by the biggest spender in OECD, which is the US. So China is increasingly putting a lot of money into development of technologies. Another way of looking at innovation and measuring it is outputs, what comes out of the innovation process. A lot of the economists spend a lot of time looking at patent data. And on one hand, this trend of patent data from OECD, patent database shows what you'd expect, which is as climate change has become more high profile, there has been an increase, a very sharp increase in patenting activity on many low carbon technologies, renewables, carbon capture and storage is much lower in the orange there, and a number of other technologies which are associated with low carbon infrastructures like hydrogen. But I think there is, again, some health warnings here for this data. Many technology developers do not patent what they find, so there's a lot of innovation goes on which isn't patented, so it won't show up in this data. And if you look at the detailed research evidence on that, there's lots of examples of it. And the second is looking at raw patenting numbers, you could get a skewed idea. So, for example, in China, Chinese patenting has accelerated very rapidly in the last few years, partly because of incentives for researchers to patent. But it doesn't necessarily mean those companies and those researchers are actually catching up and are now at the forefront of research in particular technologies. That really varies quite sharply across technology groups. So patents are useful, but again, you need to be clear that they're only a partial answer to the question of what's going on. Final measure, which we talk about in the book, is outcomes, investment. Where is investment going? This really mirrors one of the graphs that Jim showed again from IEA, looking at investment in the power sector globally on some of the renewables. Clearly you can see acceleration. Some of that, of course, is mature technologies, but some of that is very much due to the interplay of public policy, innovation, and deployment. And certainly, until you look at it recently, it's getting up to about 50% of total additions of capacity in those countries that are shown there. So that's just some more data that you can use to look at what's going on. So finally, what does all this mean for public policy? Well, clearly what we find in many of the individual cases and across the board is that government policy has a very significant impact on the level and direction of innovation. Government policy, obviously, in a climate change mitigation direction, but also government policies, for example, in the US, that is encouraging things like the shale revolution, whether it's R&D or the particular set of policy institutional arrangements that were in place that allowed that shale gas revolution to take off. So not all government policy is pointing in the low carbon direction, but it has a very big influence nevertheless. I think an important thing for the negotiators, when I was advising UK and EU negotiators, a point that we always made very strongly, is that technologies aren't owned by the negotiators. Often they talk as if they are. Actually, the energy technologies are owned by firms and by research institutes, so they've got to put together packages of finance and technological incentives that persuade those companies to collaborate and deploy those technologies in the way that's desired. But they don't own those technologies and they can't trade those technologies directly. Thirdly, I think there's a lot of evidence out there that government spending should be increased on R&D. Compared to many other sectors, the energy sector does not spend very much money on R&D if you compare it to pharmaceuticals, ICTs. Partly those industries are structured very differently, but R&D intensity is very low. But I've put the Apollo program front cover on there, really to make the point that we don't need to pour loads and loads more money into fundamental R&D if we want to meet our climate targets. Of course, as a researcher, I'd welcome that, but I think it's really important to not lose sight of the incentives for demonstration and deployment of the technologies we already know about. And if we lose that, then we're certainly not going to meet the challenges that we have. And then finally, if governments are going to get into the business of increasing spending and directing that spending, then it's important to have sufficient capacity to understand how do you make choices about which innovations to support, because not all countries can support all technologies, but also how do you learn from successes and failures? How do you give industry enough space to succeed and fail and experiment, but how do you learn from that and adjust your priorities accordingly? So I'll leave it there.